Hi everybody, you've been asking a lot of great Algebra 2 questions, so I suppose there's no time like the present to review. Let's do a couple of homework highlights, and I hope that this will help you think about some of the prior material. So question number 3, it says, given the points 3, 4, and 180, create a bunch of models that go through the points. So a lot of people asked, well, some people asked about if you've got a quadratic model that doesn't have a third point, how do you deal with that situation? So here's what the 2 points look like in Desmos. Remember that there are a whole bunch of different quadratic curves that go through those 2 points. So like here are a lot of them. So an easy thing you can do is just decide where you want the third point. So for example, let's say that I decided I wanted my y-intercept to be 10. That would be really easy because that would let you just directly solve for your c value, because you know that c is 10. And now you could use your other points to plug in and solve for a and b, and you'd get that curve. Maybe this curve, if you had other data, maybe this curve isn't the curve you want. Maybe you'd want to substitute a c value of 2, plug in your other points, and then you'd get a curve more like this. The main thing that I want you to focus on, though, is like these little bumps in the road. Like, you shouldn't let these be impediments to you. Like, you should really use your common sense to think about, okay, I want a quadratic model that goes through the 2 points. Doesn't give me a third point. Let's just choose one. I think you guys are too much in school mode and not enough in like thinking about solving problems mode. It's good to be able to think through the situation algebraically also, though, so let's go through that. So let's say we've got our general quadratic model and I substitute in the xy values. Remember what substituting actually means. If I have 3 numbers a, b, and c, depending on what those numbers are, I could literally make the curve look like any quadratic. I could make it pass through any points I wanted. So when I'm substituting xy values, what I'm doing is I'm saying, I want to find numbers a, b, and c so that it makes this equation true. And what it means to make that equation true is it's forcing the curve to pass through the point 80, 100. If I'm finding a, b, and c, which make this equation true, I'm forcing the curve to pass through the point 3, 4. A lot of people are isolating a variable and substituting. I think very often it's going to be faster to eliminate a variable. For example, in this case, if I subtract the second equation from the first, I get c minus c, and now I've eliminated the c. So let's see, 100 minus 4 is 96. Here I've got 80 squared minus 9, because that's 3 squared, so that's how many a's I have. I've got 80 minus 3, which is 77b, and then the c's go away. So at this point, I've got 2 directions I could go. I could solve for a in terms of b, or the other way around. So you can do those algebraic steps on your own, because that's basic algebra. But let's go ahead and take each of these and use them to solve for c as well. So let's pretend that I know what a, so like if I knew what b was, I could plug it in and I could figure out what a was. Let's solve for c also in terms of a. Sorry, b. So if I substitute this equation in for the a in my second equation up here, what do I get? Like, I'm isolating c, so I'll have 4 minus 9 times a. So that's my a, but my a value is coming from here. And then minus 3b. So that would be my c value. Over on the other side, I could do the same thing. Let's pretend that we're taking that equation, only now we're going to substitute in for b. So I'd have isolating c is going to be 4 minus 9a minus 3b, but now my b value is given here. Like that. Okay, if I substitute all of those back into my original quadratic, it got a little squooshed here, but you know what it is. So my original a times x squared plus b times x plus c has now become, oops, this whole term is the c term now. So I've now got an expression in terms of b as my initial coefficient, then I've got b, and then I've got an expression in terms of b. So really, my b value is the only thing I'm changing, and depending on what number I choose for b, it forces all 3 of the numbers to be something specific. So let's give it a try in Desmos. Here I've got ax squared plus bx plus c. I'm going to substitute for my a value what we'd solve for, 96 minus 77b divided by 6,391. My b value is just whatever it is. And my c value is, what was it? 4 minus 9a minus 3b. Except remember, my a is really now determined by this expression. So I could retype that whole expression, but Desmos makes it a little bit faster. All right, great. So now I've got this model. So now if I drag my b value around, you see I'm getting a whole bunch of different curves that are both forced through those 2 points. A great extending question for you to think about is, could you go through this same algebraic process, but make it so that c is the only parameter that could change? So in other words, you choose so like I'll have the c value be a slider. You've solved for a in terms of c and b in terms of c. And so now you can just choose what you want your y-intercept to be, and the other 2 coefficients will automatically set themselves so that they go through those 2 data points. Okay, let's do question 2. So this is some data for how long does it take to fold an origami model depending on the number of folding steps. So as you'd expect, the more folding steps there are, the more time it takes to fold the model. But we want to be able to interpret these graph features very specifically in context. So part A, what does the y-intercept of the red model mean? It looks like the y, let's see, the scale here looks like on the y-axis each grid mark is 10. So since this is about halfway up, it seems like it's about 5 seconds. But it corresponds to 0 folding steps. So the y-intercept means that for a model with 0 steps, it will take 5 seconds to fold. And that doesn't seem very realistic. Part B says the blue model is BF and the red model is RF, and we see that BF is larger than RF. So remember, those are talking about the y values. So we're saying, so really this math is just saying the blue curve has a height that's bigger than the red curve whenever our input variable f is larger than 1. And that's just visually obvious here. But what does it mean in context? Like literally think about the meaning of the x and the y separately. So what we're saying is when f is bigger than 1, so when the number of folding steps is larger than 1, the blue curve will take more time than the red curve. Or in other words, the blue model is taking more time to fold than the red model. Okay, the next question asks, what is the approximate slope from 8 folding steps to 9 folding steps for the blue curve? So let's see, 5, 6, 7, 8 is this point, and then at 9 folding steps we've got, it's approximately there. So let's see, the scale was 10, so I'm going over by 1 folding step and up by 10 seconds, 20 seconds, 30 seconds, 35 seconds. So the approximate slope there would be 35 over 10, or 3.5, but the units are seconds per folding step. Oh, did I say over 10? Sorry, that's over 1. So the approximate slope would be 35, but the units are seconds per folding step. So from folding step 8 to 9, it looks like the time it takes to fold each step is increasing at a rate of 35 seconds per folding step. But you'll notice that between 2 other folding steps, we've got a shallower slope. So that would mean that the time it takes to fold each step is different at that point, and so the rate at which the time to fold each step takes is increasing. This question asks, what average speed do you need to drive to get to Buelton, California from Sunnyvale within T hours? I hope you looked up where Buelton, California is. It's a cool place. So as a model, we're interested in what speed is required as a function of the time we want it to take to get there. So if we were going to think about this conceptually, if we wanted to take 0 time to get from point A to point B, we'd require infinite speed-ish. If we don't care how much time it takes, if it takes an infinite amount of time to get there, we could go 0 speed. That's fine. That's very conceptual, but if you wanted to think about what kind of sense does that make on a graph, we're saying as the time we want it to take approaches 0, we got to go faster and faster. So if this is speed and this is time, we're saying as the times approach 0, we want the speeds to get faster and faster and faster, approaching infinity. If we don't care how much time it takes, if the times are approaching infinity, then it's okay for our speeds to approach 0. And if you think about it that way, you know a family of curves that fits this picture. It's the 1 over t family of curves. A different approach would be to remember that distance is your speed times your time. That's how you calculate distance. So if we reorganize that to solve for time, we've got time is distance divided by speed. But in this case, distance is constant because it's the same distance from point A to point B, no matter how fast we want to drive. Wait, did I solve for this in the wrong way? Yes, sorry. That would be solving for time as a function of speed. We want to solve for speed as a function of time. So same thing, d is constant. We're solving for s as a function of how much the speed as a function of how much time do we want it to take. And sure enough, this model fits our conceptual idea of what it should have looked like.